Let us now simulate this model of the induction motor, this dynamic model of the induction motor in the Octave simulation environment and simulate the induction motor model. On the left side here in this directory, you see that I have two files, sim.m and model.m. And model.m contains the motor model. So we know the syntax in which we are writing model.m. We go along those lines, and these are the state variables. I will explain that. The state variables that I'm using here is is alpha, is beta. Because I can't put alpha and beta, I am using A and B symbols. Is A, is B, IR alpha, IR beta, and omega m are the 5 state variables. Likewise, if you see here on the right hand side in the model, is alpha, is beta, IR alpha, IR beta, and omega m here, d omega m by dt. These are the state variables. So it's the same model that I'm trying to implement. I have taken a typical induction motor in the lab which has these parameters. So I have taken these parameters to simulate an induction motor which is there in the lab. I am using some intermediate variables here, ls1 and lr1, and it basically represents lss by m minus m by lrr for ls1. So you need to represent this LSS by m minus m by LRR, and likewise m by LSS minus LRR by m for this portion. So therefore it becomes easy for you to write down the equation. So the first step is the input here. We need to generate the voltages. The voltages are 3-phase voltages coming from an inverter. U phase, V phase, W phase represents the R, Y, B phase or the A, B, C phases, the 3 phases. So U to 0 is from the phase to the center point of the leg of the inverter. V to 0 is the V phase to the center point of the leg of the inverter. Likewise, VWO. So these are the 3-phase waveforms generated. This is a function which is there in the library. Vm is the peak voltage, 325 for the phase voltage, Fs is 50 Hz and time t. So from this phase to pole voltage, we will generate the phase to neutral voltage. We have seen in the DQ axis theory how to do that. And these are the equations to give the phase to neutral voltage. And from the phase to neutral voltage, the 2-phase orthogonal Vs alpha, Vs beta are obtained using this equation. Again, we have seen this in the DQ axis theory. So that will give the input Vs alpha, Vs beta to the model of this induction machine. Then comes the dynamic model of the induction machine itself, which we are writing next here. The is alpha dot, this is alpha dot, is beta dot, ir alpha dot, ir beta dot, and these are the 4 equations which represent the model of the induction machine. Is alpha dot, is b dot, is ir alpha dot, and irb dot. And then there is one more differential equation, omega dot, which is basically the torque and omega relation dynamic equation. So that is this equation. So you have 5 state variables, which means 5 d by dt's. So which I am writing it here, is a dot, is b dot, ir a dot, ir b dot, and omega m dot. And these variables are sent as x dot as output to this function, which is this x dot here. So here the states that are passed, x that is passed into the function as input are assigned to the state variables isa to 1, isb to 2, IRA to 3, IRB to 4, and omega m to 5 in the same order that we are passing them out. It should be in the same order. So this forms the dynamic model of the induction machine, which is placed in this model.m file. Finally, there is one statement here, scope it. I am scoping the load torque TL. So the load torque is actually generated here. Load torque is 10 Newton meters into. So this goes high, that is for t greater than 3 it will go high, and for t less than 4 seconds it will go low, which means for the period between 3 seconds to 4 seconds there will be load torque applied, a step load torque applied, and the value is 10 Newton meters. So this is the load torque. We can have a look at it in the waveform. The other waveforms that we will see, of course, are the state variables, and we need not see all the state variables. Let me open the sim file. When you open the sim file, you have the sim file here on the right hand side. It is of the standard template where the final time is 5000 milliseconds or 5 seconds. And in order to display, we are displaying 3 state variables, not all 5 state variables. State variable 1, state variable 2, and state variable 5. And in addition, we are also displaying the scoped state variable, which is the TL. So if you compare with the model file here, the first state variable is nothing but IS alpha. Second state variable is nothing but ISB or IS alpha. Then the third variable to display is state variable number 5, which is nothing but omega m. So we are displaying that. Plus you are also displaying the scoped variable, which is TL, load torque. So that is here. So we can probably bring in some clarity in the display by giving labels. So let us say I will label the first plot is ISA, the second plot is ISB, the third plot is omega m, and the fourth plot is the load torque TL. Let me save this, and we are ready to simulate this. So let me go into Octave, and from within Octave, first let me do package load lu helper underscore sim. You have to load this helper file so that you have all the helper files for simulation. Now go to the directory. I will go to the work directory. I will go to the induction motor. You are in the induction motor folder where you have the 2 files, sim and model. Now I will run sim. Run sim. So you will see the simulation is getting executed. There are 4 plots. You have ISA, ISB, omega m, and TL. So you will see that this dark blue plot that is where the ISA, ISB, IS alpha, IS beta, the 2 orthogonal phase currents, and this red plot here is of speed. It goes and settles at 314 RPM, radians per second. And here you see that at this point, at 3 seconds, you have a torque of 10 Newton meters being applied. It continues till the 4th second, and the torque is removed. So it is a step application, pulse application of the torque. So during the torque, the stator current increases, which is again expected, and there is also a drop in omega, because you have B omega. There is a friction loss, and friction into omega is friction is into omega, and as the load changes, omega changes, you will see a change in that drop also, and as a consequence there will be variation in the omega in the open loop. If you close the loop and have a reference frequency, there will be automatic slip correction due to the controller, and this speed will be held constant at any desired value. So if you zoom in, you will be able to see, let me see this portion here. So when I zoom in, you are seeing the alpha and the beta component of the currents, stator currents. They are sinusoidal in nature and varying from 0 to 40 amps depending upon the load. Now this is here, the speed is ramping up. So if you look at the speed is ramping up, here the load is d omega by dt, j d omega by dt. There is a d omega by dt. During this time, the load torque is the axle is the inertial torque, wherein the machine is being brought to a stable speed, and j d omega by dt has to be overcome. So that is that current. Now here a stable speed is reached and there is no j d omega by dt torque, and therefore the currents are very low. And at 3 seconds there is an external torque applied, TL of 10 Newton meters, and there is an increase in current. Also at dip, change in j d omega by dt due to the factor drop b omega changing. So this way you can study the induction motor, you can expand it and get a much better insight into the various waveforms and wave shapes, and you can probe the various state variables and understand the induction motor. So this is a simulation that you would see in the Octave environment, where you are directly simulating the equations of the induction motor model here. So this is direct simulation of the induction motor model, the 4 state variables plus the omega variable.